I'm gonna learn some non-linear stuff. I'm gonna do some math. I think. Not don't know what exactly I'm gonna do, but I think I have an idea of what kind of gooning strategies that I need to engage in. I think a lot of let's look at some math law. Math only goofing off, nothing serious. Your mathematics and its application. Okay.
The beginning of mathematics starts with numbers and counting, which at one time humans did not know anything about. One of the age-old questions actually is, did we invent numbers, or were they already with numbers and counting, which at one time humans did not know anything about. One of the age-old questions actually is, did we invent numbers, or were they already there? Now, of course, we use a 10-digit number system, but there's no mathematical reason for that. There's no reason we could not have 9 digits, which means after 8, the next number would be 10, because you'd be out of digits, and you would need to reset the ones place to 0 and then add a 1. This would represent what we know of as 9 if there were 9 digits. We believe that the 10 digits comes from the fact that we have 10 fingers. Simple as that. In fact, there are many times we only use 2 digits. It's known as binary. But mathematicians actually say had we picked 12 digits, then arithmetic would be much easier, considering 12 is divisible by more numbers than 10. One of the oldest foundations of mathematics, which is lost on many people today, is logic. Although a lot of advancements in this field were done in the 19th and 20th century, it started around 2,500 years ago. In a logic class nowadays, you'll notice some odd examples of problems that involve just thinking. For example, take the sentence, if it is raining, then the ground is wet. Let's say that is definitely a true statement. Now, is this next statement also true? If the ground is not wet, then it is not raining. Anyone who's learned basic logic, which even includes various geometry students, can answer this in a second. Others may need a little more time, but these two statements are in fact logically the same. In fact, whenever you say if something, then something else, it is always the same as saying if not the second thing, then not the first thing. If an angle is 40 degrees, then it is acute, and if an angle is not acute, then it is not 40 degrees, are logically the same thing. Concepts like this may seem weird, but within mathematics, we need very formal language that we all agree on in order to prove theorems that are extremely difficult to understand. If you were asked to prove the statement, if x squared is even, then x is even, you now know you could also prove if x is not even, then x squared is not even. Proving one automatically proves the other, and although this is an easy example, when dealing with more advanced mathematics, we need a very clear understanding of the language and logic behind every statement. Then a little later, just over 2,000 years ago, the mathematician Euclid published a series of 13 books known as Elements, which many regard as the most influential textbook of all time. While there's a lot discussed in these books, one important concept is the Euclidean algorithm or Euclid's algorithm, one of the first mathematical algorithms ever discovered. An algorithm is simply a series of steps that solves a problem, executed often but not always by a computer. This algorithm calculates the greatest common divisor of two numbers in an efficient way. So if you want to know the largest number that goes into, let's say, 714 and 1054, it would not be that hard, but may take a little bit of time to find the answer is 34. Instead, we can use the algorithm. I'm not going to explain how it works, but it just involves basic elementary school arithmetic, and using it you can probably figure out the answer by hand in less than a minute. I mention this algorithm because it extends to the field of cryptography. Cryptography is really about techniques that ensure secure communication, especially in the presence of adversaries such as hackers. When putting sensitive information online, let's say, normal text is encrypted using mathematical techniques that turn it into text that cannot be understood by a third party or really anyone, at least until it is decrypted back to original text, which you need a secret key to do that only the receiving party should have. Although there are various methods of encryption, certain types such as RSA rely on the fact that it is very difficult to break large numbers up into prime factors. Cryptography heavily involves number theory or the study of integers, which is why that Euclidean algorithm from before has applications in this field. This is what protects our passwords, credit card numbers, and any type of sensitive online information. In fact, the NSA, or National Securities Agency, is the largest employer of mathematicians in the United States, as they need those mathematicians to create and break these codes. You may think cryptography is a recent development, as computers have not been around for even a century yet. However, it dates back hundreds of years where written letters were encrypted for privacy purposes. In fact, techniques to decipher these encrypted messages were used on messages from Mary, Queen of Scots, which revealed that she had sanctioned an attempted assassination of Queen Elizabeth, and she was executed shortly after that in 1587. Moving on, there were of course several hundred years of discoveries that we all know of very well. For example, the discovery of pi, which actually took a lot of work to pinpoint exactly. It was approximated as 3.125 and also 3.16 for a while, until several years later better approximations were made. Then logarithms, geometry, algebra, basic Cartesian coordinates, and complex numbers, which I made an entire video on, and so on were all discovered hundreds to even thousands of years ago, so I'm not going to cover those in any detail. But if you want a random fun fact, the radius of the Earth was approximated in the 3rd century BC to nearly 99% accuracy using basic geometry, deductive reasoning, and just measuring a shadow length. But with that said, now I'm going to jump ahead to the 17th century when calculus was introduced. To the world, which would change math and physics forever. Newton was concerned with analyzing rates of change not as an average, like average slope, but at one instant. This instant rate of change became known as a derivative, telling us the change in some parameter with respect to another at, again, one specific instant. For example, if your speed is constantly changing, algebra can tell you the average speed, but calculus can tell you the exact speed at any moment in time, kind of like what a radar gun would read. This gave us much more powerful insights to the motion of planets and how they change their speed throughout an orbit. Then the motion and behavior of electromagnetic waves is expressed through calculus. Moment of inertia, or essentially an object's resistance to rotation, is calculated using calculus techniques. And calculating the work done on a particle moving through a complex vector field requires calculus. Calculus is used within economics and maximizing profit, chemistry and calculating diffusion rates, and so much more. There's no way to do justice for all the applications of calculus, but whether you study engineering, physics, math, chemistry, bio, or even business in college, unless you have all the needed credits, college will start with a series of calculus courses to be used later on. Next, in 1736, Leonard Euler published a paper on the 7 bridges of Königsberg, which is regarded as the first paper in graph theory. The question was quite simple. Given this network of bridges, can you cross each bridge exactly once, of course without going into the water? You can try it for yourself, but spoiler, Euler eventually proved it to be impossible. Graph theory is not about the graphs you know from middle school and high school. A graph here is made up of nodes and edges that connect them. This could have a wide variety of applications, many of which lie in the field of computer science. Now, a graph can have nodes that represent people, and their connections could represent compatibility, in which dating sites need to use algorithms to create best matches. Nodes could be cities, and edges are routes that connect them. We need to figure out the shortest path from one point to another. Or a graph could represent how we're all connected through social media or another social structure. This investigation is known as social network analysis, which is used, for example, in security applications to map out information on street gangs, terrorist organizations, and more. To end this subfield and emphasize how powerful graph theory can be, it has made two computer science graduates, Larry Page and Sergey Brin, billions of dollars. In the 90s, they used graph theory in such a way that nodes represented websites on the internet, and if one website linked to another, that would be represented by an edge. The more links going to a website, the quote better that web page would be considered. This algorithm to rank web pages became the backbone of what is now Google. Out of Euler's Seven Bridges of Königsberg paper, not only came graph theory, but also the field of topology, one of the most advanced math courses you would take if you studied math as an undergrad. In topology, you have to forget about the notion of lengths and angles like in geometry. In this field, you care more about connectedness and holes, for example, where bending and stretching is totally fine and does not change the properties of the space that we care about. For this reason, in topology, they famously say that a donut and a coffee mug are the same thing. The questions of can you morph one object into another, or whether the two are homeomorphic, is important within topology. You'll analyze complex shapes, higher dimensional objects, knots, and so on. This class allows you to understand the mathematics of things like cutting a Mobius strip in half, which I did in a previous video. Or reveals mathematically how you can turn a sphere inside out without cutting or tearing it or making any creases, while yes allowing self-intersections.
Is this it? Is this a sphere turning inside out?
Topology applies to fields of physics such as quantum field theory or cosmology, and general relativity states that spacetime is a four-dimensional Lorentzian manifold, and analyzing this involves concepts within topology. In robotics and motion planning, all the possible states that the robot can be in, or the configuration space, can be modeled using concepts taught in topology. In computer science, topology can be used to model how networks are connected and how data flows, and even knot theory is used in biology to analyze how enzymes cut and reconnect DNA.
And I also have the possibility to steelman you. So all the algebraic topologists who just heard, for characteristic not equals to 2, they're like saying, yeah, that's fair. And so in part, by just jumping into the middle of this, we don't have the benefit of putting your best foot forward because, if you say 1 times 1 equals 2, everybody knows that that's crazy. But what you actually may mean, and what the fact that you don't use certain terms or the fact that you use certain pronunciations that communicate to me something very positive, which is that you taught yourself. You learned this stuff from reading about it because nobody taught you or you wouldn't pronounce. Pronounce certain words the way you pronounce them.
True.
Yeah.
True.
So, in part, you always have the ability to make fun of somebody who pronounces a word the way it's read on the page. And then, you also have the opportunity to say, holy cow, that guy actually taught himself. That's more impressive.
The thing about math, right, especially if you're talking about pure axiomatized math, the experience as a student is that you are going through a textbook and it starts with saying, here's the axioms of this field. And then we're going to deduce from those axioms like various different lemmas and theorems and proceed from that. And with that as the framing, you get the impression that you could have just come up with any axioms. Right? You just make up some pile of axioms, deduce what follows from them, and the space of possible like math is unfathomably huge. And so you need some process that culls down what are the useful things to maybe pursue. And so one of the things that I think is all too often missing in those pure math textbooks is basically the motivating problem. Why is it that this was the set of axioms people found to be useful and not something else? The framework for quantum information theory, it's like you marry together linear algebra and probability, and that's great. But there's all sorts of other things where you could kind of try to cram them together and maybe get some sort of math out. And the question becomes, is it worth your time to do that? The thing about math, right,
So are there really 3 hours of questions? Or has it? Are you fucking serious?
Yeah.
You don't think there's a lot to talk about, Elon? Holy fuck, man.
These are the graphics from Unreal Engine 5. They're quite good. The engine is simulating physics so well, sometimes it could be hard to tell the difference from reality. And to accomplish this, something that is absolutely essential is numerical linear algebra, or NLA, which is a study of linear algebra applied with computers, and is better labeled applied linear algebra because that's really all it is. Now without it, there are no good computer graphics. Mapping 3D objects to the 2D view screen? That's gone. Rotating those 3D objects? Gone. Rasterization, where triangle vertices are used to determine pixel color intensities? Also gone. But seriously, all it is. Now without it, there are no good computer graphics. Mapping 3D objects to the 2D view screen? That's gone. Rotating those 3D objects? Gone. Rasterization, where triangle vertices are used to determine pixel color intensities? Also gone. But seriously, without NLA, a lack of video games would be the least of our problems. We also wouldn't have weather forecasting, many types of data compression, finite element methods for stress testing, compressed sensing for MRI, fluid dynamic simulations, recommendation systems, search, and of course, deep neural networks. An argument from one of the leaders of the field, the late Jean Golub, was to point out that of the top 10 most important algorithms of the 20th century, 6 of them related to numerical linear algebra. And that was almost 20 years ago. Now, I decided to make this video when I stumbled upon this paper, Randomized Numerical Linear Algebra. In it, I found some remarkable claims. They show how some well-placed randomness can speed up some NLA algorithms by an order of magnitude. In other words, we're looking at a potential breakthrough in scientific computing. And randomization for speed seems like a really bizarre idea. Why would an algorithm that wants to compute something exactly be super sped up by doing something akin to coin flipping? Now, to fully appreciate this, we'll need some background. But first, this episode is brought to you by True Theta, the data as an arrow. Now, this is just a wimpy 2D vector. The powerful stuff comes from using n-dimensional vectors, which can represent complicated things. Everything from images, to words, to audio, to a person's credit profile. Basically, most things you can think of can be represented as a vector. Now we consider a matrix. On the surface, a matrix is just a grid of numbers. Or you can consider it a list of vectors. As a list of vectors, you can imagine it as a bunch of arrows. When a matrix represents data, they're commonly represented as points. But in linear algebra, matrices represent something else. They relate to functions. In our case, a function is something that receives an input vector x and gives back a vector y, possibly of a different dimension. And it needs to do that for a range of x values. If we were to increase the dimensions, the function would be connecting exponentially huge regions. In this sense, functions are very information-rich objects, since they represent an enormous set of connections. But handling all that information explicitly is often impossible. So we make a fantastically liberating assumption. We assume the function is linear, which means it's like a line or a plane or something similarly flat in higher dimensions. More rigorously, linearity comes from some algebraic properties, but we don't need to get into all that. What's important is why linearity is useful. Consider two cases, where the inputs and outputs are both one-dimensional. In both cases, suppose we'd like to guess the function, after being shown two input-output pairs. Now, on the left, we don't make any assumptions about the function. It can be any function. On the right, we assume the function is linear. With this, can we determine the functions? Well, when we assume linearity, yes, it's easy. There's only one linear function that goes through these 2 points. But without the assumption, there are infinite functions that pass through those 2 points, and we have no way to pick one. This is totally essential. Linearity allows us to determine these information-rich objects, functions, with very little. Basically, to know a linear function in one region is to know it in all regions. This fact is so useful, much of applied mathematics involves making a linearity assumption wherever we can get away with it. Doing so allows us to extrapolate in space, or time, or something else. And crucially, it makes the exceptionally powerful theorems of linear algebra available to the problem at hand. If we assume linearity, we essentially get an instruction manual for computing useful things. So how does a linear function relate to a matrix? Simply, if f of x is a linear function, then f of x equals a time
The secret to sustainable
times x for some matrix A. Saying A times x is to do matrix multiplication, which is a simple but tedious calculation of sums and products. Please don't think about the details. Okay, now we can ask, what is numerical linear algebra? Well, that's the study of applying linear algebra fast and efficiently with computers. This brings 2 fundamental challenges. The first is the computer's finite precision. The second is that fast algorithms are machine dependent. Let's start with the computer's finite precision. If a point is selected at random, it almost surely can't be represented exactly in the machine. The machine will have to truncate it to an approximation, creating a small error. This fact, as harmless as it seems, horribly complicates everything. One effect is, to a computer, addition isn't always associative. Sometimes, adding numbers A and B before adding to C doesn't give the same answer as summing B and C first. And when an algorithm fails to anticipate issues like this, it's prone to incorrect answers. We say such algorithms are numerically unstable. Now we consider the second challenge, that fast algorithms are machine dependent. Let's say we want to second challenge. Such algorithms are numerically unstable. Now we consider the second challenge, that fast algorithms are machine dependent. Let's say we want to multiply two matrices A and B. By how matrix multiplication is defined, the resulting matrix is the sum product between every row of A with every column of B. That's how it's defined, but how is it computed? Well, it helps to imagine it like this, where we are looking to fill up the cells of this matrix C. Each cell corresponds to a combination of a row of A with a column of B. From here, there are several ways we could order the computation. One way is we could finish the computation of each cell of C before moving on to the next cell. That's probably how you do it after you heard my definition. But there's another way. We could proceed like this, finishing the use of each column of A and row of B, which is swapped from how I define matrix multiplication, but gives an equivalent answer. And there are other ways of ordering operations. The problem is, ordering makes a difference for the algorithm's speed. They bring different amounts of data movement and differing data accessing patterns. And this speed depends, at the least, on A and B's dimensions, how they are physically stored in memory, and how much can be stored in a processor's registries, which are very small but provide extremely fast access. And this is just one flavor of the algorithm's machine dependence. Everything from the memory layout to the processor to the operating system to the capacity for parallelism determines the algorithm's speed. And these things must be anticipated in all their diversity across users and time to design the best NLA algorithm. As you can imagine, this gets very complicated very quickly. To appreciate what's offered by randomized NLA, we'll also need some history. John von Neumann is often named when discussing the origin of the field, because in 1947, he and his co-author Hermann Goldstine published one of the earliest uses of computers for applying linear algebra. But this isn't a relevant origin for modern NLA software, since the programming paradigms of the 40s and 50s were just so different, very little of it persists today. The code was terribly verbose, machine-dependent, hard to share, and just an absolute headache to write. So in 1957, IBM created the Fortran language, designed to ease programming for scientific
Back in 2017, when I was just 16 years old, I was browsing YouTube when I stumbled across this video, making Minecraft in C++ and OpenGL from scratch. C++ and Minecraft were my biggest passions, so combining them would be a dream for me. But I needed to go from level 0 on OpenGL all the way up to level 4 out of 5, at least if I wanted to finish this project. So I started with Studi first, and after that I was ready to start learning OpenGL. That summer during my holiday, I spent all my time doing OpenGL tutorials one by one, until eventually I finally placed my first triangle on the screen. What I didn't know at that time is that I was only level 1 out of 5 at that point, with more difficulties to come at every step. But it didn't matter, because I wanted to make that project become a reality, so I pushed on, with every game I made getting me closer to my final goal. So let's look at the 5 levels of OpenGL learning, see where you are right now, and I will give you some tips to get you to the next level. Starting with level 1, you have a triangle, but you don't understand shit. Congratulations, you placed your first triangle on the screen. This is your first ever OpenGL project, and at this point, you don't understand out of it. You have to spend like 3 days copying OpenGL code, setting up buffers, shaders and libraries, only to realize that you don't understand anything. But who cares, you have that damn triangle. It was a hard battle, but you earned your well-deserved victory. You try to impress a girl with your triangle, but she asks what kind of buffers you use, and you have no idea what that even is. But that's okay, it was just a dream. You are not talking to girls in real life if you learn OpenGL. But if you are right now stuck at level 1, like you don't have a triangle or you have a triangle, but you don't understand anything, check out my course because it's specifically made to get you from 0 to level 2 in the most detailed and easy way possible, with challenges and quizzes. Eventually, you still have the same triangle on the screen, or maybe some very basic 3D thing, and you still don't talk to girls in real life. But now, you understand what's happening under the hood. You understand now how data is sent to the GPU, how a shader works, and how the OpenGL pipeline works. All that weird stuff that didn't make any sense now is almost second nature to you, and it feels great. You really feel accomplished, like a big OpenGL weight was lifted off your shoulders. Don't get too excited, you still can do anything remotely useful with OpenGL. And 3D Math is still kinda scary, but on the other hand, because you actually understand what things do, you can get to practicing on your own, and very soon you will get to level 3. Level 3, you can do 3D. This is the scariest part for most people, but right now, you just got past it, and it doesn't even seem hard anymore. And not only you finally understand 3D, but you actually have a mini-game engine by now, with lighting, materials, maybe even some physics. Now, I know for a fact that if we look under the hood of that engine, we will see only OP crap, like every texture is a shared pointer, and you need 15 hierarchies of classes just to draw a single triangle on the screen. But let's not look at that. The important thing is that learning is super fun now. The 3D mess is satisfying now that you understand it, and the lighting is very cool to experiment with on your own. You can now complete some cool chapters in learnopenGL.com. Lights and textures are easy. Normal maps or shadows are little difficult, but who needs those anyway? If you spend a little more time, you can maybe add a skybox to your engine, and no one will notice how bad things look. But who cares how bad it looks? You have a 3D game, how awesome! And by now, you also stumbled across level 5 articles that look cool, but you absolutely have no idea what they mean. You still show them to your friends regardless, so you can look smarter than you are. But after a while, things are not fun anymore. All the easy chapters have been completed, so now only the hard tasks remain. Maybe you get lucky enough to stumble across this video made by a very smart guy that is totally not me, to get some more easy to implement ideas. But that only gives you 1 or 2 more days of coping, before you have to face your biggest fear: implementing the not so easy stuff in OpenGL, like doing shadows, PBR or animations. The more you postpone that, the more you realize that's the only way to get to the next level. But one day, you'll finally start looking into these hard topics. And before you know it, you are at level 4, Advanced OpenGL. This is where you basically can do OpenGL on your own. Things like normal maps are easy, shadows are still, but you can at least implement them. And you even have PBR in your engine. There are so many cool things to do here, like different rendering, and look at these cool PBR materials that I have. But by far, the biggest marker of being level 4 in OpenGL is the fact that you can implement your own OpenGL algorithms without looking at any tutorial. I promise that I will eventually get to make Minecraft in C++, so I started to work on it. I needed a way to send data very fast to the GPU, and I came up with a solution to draw entire faces from a single vertex. I didn't know at the time, but this was called vertex pooling, and I implemented it all by myself. Or take a look at this God race. I tried searching online for tutorials, but I didn't understand. However, after chatting with ChatGPT a little about the subject, I realized that, bro, I can implement this myself today with no external help. Or take a look at these cool caustics that I have. I looked at how Minecraft caustics look. And then I also searched online a little until I found this video that shows how to fake caustics with a texture. So that's what I did. Isn't it cool? And I know things are hard, but you have all the resources online available. All you need to do is just spend the time, read them and try to implement them, even though it feels impossible at the moment. Maybe you even get lucky and stumble across the links in my Discord server, where I placed every good free OpenGL resource I know about. But this gets us to level 5, OpenGL God. At this point, everything you do happens in compute shaders, and these articles that you show to people to scare them, now you actually understand them, like this spherical harmonics article. These things are actually not that hard, and are used to very cheaply encode global ambient light. But what the f is this, bro? And I want to tell you an interesting story. Not too long ago, I met this guy who makes this very cool voxel game. Technically, he uses Vulkan, not OpenGL, but he's clearly a level 5 graphics programming god. The techniques and things he does are insane. This demo that you see runs at 120 FPS. Rendering 18 quadrillion voxels. He has implemented both the ray tracing version and the classic rasterization version. And check this optimization out. Because blocks basically become 1 pixel at high distances, he draws them with a special compute shader that fills the screen pixel by pixel, rather than rasterizing them. This optimization was literally inspired by Nanite. Literally the latest and probably the most complex optimization from a real engine. Or the geometry cooling that he has is insane. I can't even understand how it works. It somehow magically reduces the geometry to only the things that are visible, all in compute shaders of course. Or for his global illumination implementation, he just basically found an implementation We are closer than ever before to the release of Silksong, and I can't wait to play. But why is Hornet getting naked? To find out, I'll make my own Silksong in C++ from scratch. And while making the game, we might just find out why is Hornet taking off her clothes. And what's even better, instead of spending 6 years, I'm going to make it in one single day. Off her clothes. And what's even better, instead of spending 6 years, I'm going to make it in one single day. Now, Team Cherry chose an inferior language called C# and Unity, but I'm going to also fix that today, by making it in C++ and using no engine. We'll also discuss whether it's better to create a game from scratch or use an engine. But let's see first if I'm up to the challenge, because I asked ChatGPT and one day is a lot less than 6 years. So wish me luck. Very similar to the Moss Grot. You might be wondering, why do I need a 3D camera for a 2D game? Take a look at Silksong. Notice how the background objects move slower than the foreground ones. This effect is called parallax. It gives this nice 3D feel to 2D games. And it's easy to implement, but to keep things much simpler, Team Cherry actually just made the game in a 3D environment. And I need to do the same. And here is where people will tell you that using a game engine will make your life easier. But it really depends. If you know graphics programming, making something like this from scratch is actually surprisingly easy. I just started with my 2D rendering library and added a matrix multiplication. This will make everything 3D, and that's about it. And look, I even added some custom shaders to blur the background objects. But I'll return to the engine versus no engine debate later. Right now we have a bigger problem to solve. I can't for the life of me find Silksong sprites to decorate the environment. I do have a graphics tablet. I could use it to draw my own sprites. But this would take too much time. Remember, start. Both in and at first, I don't want to spoil it. Before that, I have one more thing I want to talk about. You can probably see these collision boxes here. Well, I was using a physics library called Box2D, and I was too lazy to change it. But normally, for a no matter if you use an engine or not. And at this point, I would just make the game in C++, and avoid the downside of using an engine. In C++, however, you don't have this problem at all. And no, you don't have memory leaks problems either. There are some very easy things that you can do for game dev that I show in this video. Point is, both options have their strengths. Okay, I know it looks nothing like the real game, but for one day of work, I really like how these parallax effects turned out. Now, the moment you all have been waiting for. Why is Hornet removing her cloak? So she is climbing this thing, checking this nice parallax. I didn't have time to add enemies, nor have I found any sprites online, so I'll just add them in post. Show! Now what's that? It's the show from the trailer. And she's getting naked. Wait, are you seeing? In this video, I'm going to make a simple 3D game in my engine to see how difficult it is in comparison with Unity. But let me tell you a story first. And it explains why I personally don't like using Unity or other game engines. So, I was in high school, very excited to learn programming, but was struggling with the graphics part. I had enough knowledge to start working at a game, but simply wasn't able to find the graphics library to work with C++. Think about that. I was ready to start working at my passion and make my first game, but I just wasn't able to link SFML to my C++. You are not supposed to do problems that I could just store the world in a 2x2 matrix. If this sounds like you, I have some good videos to help you set up C++ for game development very easy. But fast forward. A few years. Now, I need to make a simple game for an university homework. And remember 15 seconds ago when I told you that I would make a simple game for an university homework. And remember 15 seconds ago when I told you that I would maybe learn Unity later? Yeah, that never happened. So, since I don't know how to use Unity, I'll try to use my own engine to see how difficult. Fast forward a few years. Now, I need to make a simple game for an university homework. And remember 15 seconds ago when I told you that I would maybe learn Unity later? Yeah, that never happened. So, since I don't know how to use Unity, I'll try to use my own engine to see how difficult it is. I have to make a simple game with a forest scene, animations on the player, and a simple enemy fighting mechanic. This is something that you can do in Unity in no time. And since the advantage of using an engine is that it makes the beginning easier, while I think that the advantage of running your own engine is that it makes the later part of the development easier, I can expect it to take some more time, but I'm curious how much more. So I created a new container, which is a scripting method for my engine. However, think of a container more like a Unity scene rather than a Unity script, because using a container, you basically control the entire game loop, so that means the entire game. Then I loaded my 3D library and checked that it was working properly. I took some 3D models from the web, those models being our models now of course, and added them into the scene. Now in Unity, you have a nice editor. In my engine, I had to add a bootleg water cooling system to keep it running. Oh, how did that code end up here? Oh wow, working third-person camera movement. Oopsie daisy. No, I don't want to hear that I'm cheating. You'd have also done that in Unity using the web or an asset store or ChatGPT. Up to this point, I would say that the process was not that difficult. I mostly spent my time fixing stupid little problems, but those were to be expected. I haven't tested my engine and my 3D library's new saving features that much, so I still need to work more on them. But that's okay, because the only way to improve a technology is to test it in a real use scenario. And that is basically what I'm doing here by making a game. Next, I also have to add some UI. so I could just add it by hand very easily, or flex a little by using my own UI library, which is not even ready or tested yet. So, you know what is the mature choice to make? I chose my own UI library, and well, since it was the first time that I used it for a real project, I have to say that I have to work a little more on it. But that's okay. That is why I'm testing it now, to understand how I can make it better. I realize, for example, that it is a little tedious to add and configure these UI elements by hand right now, and the editor is quite misleading. But the library works like this. I create these nice responsive boxes, and they have a name. And in the game, I will just load that would launch, and that also works with my engine. Because my 3D animation system still has some small edge cases that don't work.
The early videos in the series will focus on key elements like moving and animating the player, setting up a multi-level tile map, adding enemies who can chase and deal damage, and creating a heads-up display.
Choosing a game engine is easy, but if you're just starting out or aren't sure which engine is best suited for your needs, it can feel pretty overwhelming as you may be stuck with your choice for several months. But not to worry, because I've made a list of what engines are best suited for different kind of projects, taking into account ease of use, community size, and platform requirements. And by the end of this video, you'll know exactly what engine to start your project on. The best way to find the right engine is to try a few and see which one resonates with you the most. What I might like about Unity, you might hate, but it is important to pay attention to what with you the most. What I might like about Unity, you might hate, but it is important to pay attention to what features the engine supports, its pricing, and its programming language. If you don't know how to code, you absolutely should, or you should find someone who does know and add them to your team, because it'll really help you out in the long run. But if you're insistent on not coding because you're lazy, and no, don't come at me with excuses, you can do it, I know you can. There are some options called visual scripting, basically coding without actually coding, and the best engine for this is Unreal Engine. I know someone who made this entire game just using their blueprint system. Here's some other options you can use as well. But even with visual scripting, you'll need to learn how it works, and that's where the most important factor comes in when choosing a game engine. It's community. The more community there is, the more tutorials and help you could potentially get when you run into an issue. And trust me, you will run into an issue. Being frustrated when you can't find the answer to simple questions can easily derail your progress and take a hit on your motivation. There is a reason why 90% of indie developers don't finish their games. These are currently the biggest players in the market: Unreal, Unity, and Godot. GameMaker is also another popular option. It's important you understand that each engine has its pros, its cons, and its learning curve. Don't expect to make an open world RPG MMO in your first week while never having opened an engine before. Unity has the most resources hands down, followed by Unreal and Godot. This is because Unreal and Unity have been in the game for a really long time, but Godot's resources have been exponentially increasing over the last year. Now, the second most important thing you want to consider when choosing a game engine is what kind of game you want to make with it. Sometimes one engine is better suited for 2D, 3D, multiplayer. Choosing one which doesn't have those features built in can just prolong your development time, as you'll need to code those features yourself. So I've made a little chart to help you visualize. Do you want to make a 2D game? Unity hands down has the most features for 2D, and you can fight me about this. From tile maps to sprite editors to skeletal, I've made a little chart to help you visualize. Do you want to make a 2D game? Unity hands down has the most features for 2D, and you can fight me about this. From tile maps to sprite editors to skeletal animation, physics also has one of the best asset stores, so there's a 99% chance that someone already made the system or the prop that you're trying to create, so it's easier to just purchase it and save time. However, there is some controversy, of course, surrounding Unity, which may dissuade you from choosing it, which I'll discuss in a few moments. This is then followed by Godot, which also has great 2D support. With tile maps, collisions, it's extremely fast to open and run, has an easy to understand programming language similar to Python, pretty good documentation, and most importantly, the code is open source, so anyone in the community can contribute to the development of the engine. And lastly, GameMaker is made for 2D games. It's compact, it's quick to learn, and it's really fast to prototype. So I'm using to make my precision platformer called Boombi, which you should totally wishlist. I'm not asking. However, none of these engines are perfect, and each of them have their caveats, so it's important to keep these in mind when choosing them. But I'll mention that in a moment. So what about 3D games, or those open world MMORPG low-code? Well, this big fish blows away the competition, Unreal Engine 5. It's made for 3D and has a ton of built-in features like a first-person and a third-person controller to help get you started. Their visual coding system called Blueprints is the best in the market, and it's great for larger teams with a mix of programmers and artists. You can also download the source code and make any changes as needed per your project requirements. They give out a lot of freebies like mega scans, free monthly assets, and they even have a mega grant program to help fund your game if you get accepted. They also have great performance insight tools to help optimize your games, which a lot of beginners never worry about until they end up playing their game and realize it only runs at 10 FPS. So optimize your games, folks. Unreal is great to learn if you want to get a job in the game industry, and learning C++ in general is really good in that regard. This is followed by Unity, which has several different rendering pipelines depending on the graphical needs of the project, and Godot, which has been vastly increasing its 3D support, but still nowhere near Unity and Unreal's level. Now, to be more specific, if you're making a multiplayer game, Unreal followed by Unity is the best bet. Unreal has multiplayer built in, and the company's experience with Fortnite has trickled down to the development of Unreal Engine 5, while Unity recently introduced a new multiplayer package called Netcode, which is great, and I have a huge tutorial on, and they have Unity gaming services, which are extra options to help host servers and manage players. If you're making an open world 3D game, Unreal hands down. Optimization is built into the engine as it breaks down a large map into smaller chunks and only shows the player what they need. If you're making a physics-based game, Unity has a lot of built-in functions for this for both 2D and 3D. Unreal also has great 3D physics, but Godot's built-in physics engine still doesn't have as much features as the other two. Fellow developer Pontypants tried to start his physics-based climbing game in Godot, but ended up switching to Unity because there were just so many more components that were an easy plug and play. However, there is a popular physics package for Godot called Jolt, and I believe they're now integrating this as the main physics engine. So hopefully that will make it much better. If you're making any sort of really complicated math equations or just handling a lot of objects or AI, and I mean a lot, then you want to go with Unity, which has support for dots, the entity component system, and the job system. And if you don't know what any of that means, then you don't need to worry about it. My friend Donnie has a lot of tutorials on it if you're interested in learning. If you're making any sort of really complicated math equations or just handling a lot of objects or AI, and I mean a lot, then you want to go with Unity, which has support for dots, the entity component system, and the job system. And if you don't know what any of that means, then you don't need to worry about it. My friend Johnny has a lot of tutorials on it. It's Unity, which has support for dots, the entity component system, and the job system. And if you don't know what any of that means, then you don't need to worry about it. My friend Johnny has has a lot of tutorials on it if you're interested in learning. I want to emphasize that your first project should not be a multiplayer game, or an open world game for that matter. You should start small and just learn the basics before diving head in. Now let's take a closer look at Unreal. Unreal has always been popular and has gained even more popularity with Unreal Engine 5. It's always been a go-to choice for AAA games with big graphics requirements. It's free to use under $1 million in revenue, but over you'll have to pay a 5% royalty of your revenue for your game. You've also recently introduced a new subscription per person working on the project that only applies to non-game developers like filmmakers, and that's only once you've reached the $1 million threshold. So you'll probably not need to worry about it if you're just making games. But it's not all sunshine and roses. As with the pros, there are the cons. There is a large learning curve with Unreal. You'll have to spend some time getting used to it and navigating the million menus and buttons. You'll also need a beefy computer to even run it, and it takes a lot of space on your hard drive. There's usually a heavy reliance on blueprints because their C++ is just not fun. Their documentation is mostly on the side of lacking, and if you're changing the source code of the engine, be prepared to wait because it takes forever. Overall, Unreal is a very solid engine with a lot of great features, but you'll need a lot of patience and resilience to work with it and not give up. Now let's step into Unity's terrain a bit. Unity has always been the go-to choice for indie developers for a reason. However, in the recent years, there has been a growing dissatisfaction with them as they haven't been working on features that game developers have been asking for years. And they recently pulled a runtime fee mess where thousands of developers just stopped using Unity altogether after they tried to unfairly change their pricing. And I do have a whole video explaining what happened if you're interested. But they've since reverted a lot of those policies, even changing their CEO. And Unity still kept the notorious runtime fee, although a little different. A lot of developers ended up switching to Godot because of this, because of its open source nature. But I personally see Unity showing promise after their recent changes, and I still think it's a great engine to start learning game development with, as I once did. Unity has the most confusing pricing out of all the engines. It's free until you make $200K on your game in the year. From then on, you need to purchase the Pro subscription, which is $2,040 a year per seat. And once you reach the $1 million a year threshold, you'll also start needing to pay the runtime fee, which depends on the number of engagements the game receives. Wait, let me read this. Engagement is defined by the time a user successfully acquires, downloads, or engages with your game for the first time. Luckily, there's a max 2.5% revenue cut of your game, so you won't have to worry about it going over. Objectively speaking, 2.5% isn't bad once you reach that threshold. However, it just gets confusing with the Pro plan pricing, and it's a little convoluted. Apart from the runtime fee, they also tend to not update some packages for some time, and over the last few years, they focused on AI, VR, blockchain, instead of focusing on more game-related features for the engine. It's also pretty slow at opening projects and compiling, but I do recommend this asset to help speed up your workflow. It also gets confusing with their different graphics pipeline, URP versus HDRP versus built-in, and you have to choose one to start, and make sure you choose the right one for your project because changing later on could spell disaster. In most cases, you start with URP, and HDRP is used for more graphically advanced games. There's also no way to get the source code for the engine unless you're an enterprise and you're paying big money. However, I've never had to use to get the source code. Unity is built to be flexible to allow developers
our getting started guide here in this little tab, and we can just scene in VR. And
I'm going to teach you how to make your own games. After this video, you will be a pro. The number one lesson is your game idea probably sucks. The faster you let go of the GTA 6 in your mind, the faster you will learn. This will probably sound really harsh, but no matter how good you think your game idea is, it's probably bad. And listen, I'm not trashing on you, I'm just telling you how it is. I'm not going to serve you bullshit. Lesson number 2 is you cannot escape programming. Games are literally computer programs. You can use Visual Pro